In this video, we're going to be solving a rotations FRQ 1 for AP Physics 1. Now, we have a vertically orientated disk is mounted on a wall and is freely able to rotate about a pivot at its center. There is a massless string that is wrapped around the disk, and a mass hangs from the string. Given that the inertia is going to equal to 1/2 m times the radius squared for a solid disk, and letting md equal to the disk's mass, mh equal to the hanging mass, and radius equal to r, we want to solve the following. So this is going to be our setup. On our setup, we are going to have this circular disk mass, and then we can see our radius, and then we have this massless string attached to that hanging block. We're asked to first draw a free body diagram for the hanging mass mh. So for our hanging mass, we are going to have a downward force, that is the force of gravity equal to the weight, and then upward we are going to have the force of tension. Now, we're also asked to write the F net equation. So that equation is going to be the summation of forces is equal to ma. Summation of forces is going to be Fg minus Ft is equal to ma. The reason is we're going to consider the downward direction to be our positive direction and our upward direction to be negative, which is why we have our Ft as positive. And we are going to convert this to Fg is equal to the mass that's hanging times gravity, and Ft is going to be equal to Ft. And we still have mass times our hanging mass is going to be our hanging mass times our acceleration. We can call this Ft to stay consistent. Our torque is only going to come from our tension, which is going to be at our radius. We can draw a radius here to see that more clearly, and that's going to be at 90 degrees for our theta. Torque, as a reminder, is equal to force times radius, or here, which is our radius, but this is usually your lever arm. In this case, our lever arm is just our radius, which is the distance from our pivot to our point that we are applying the force. Now, that is going to be times sine of the angle, which is going to be here, 90 degrees. Sine of 90 degrees is equal to 1. So torque is going to equal to our force times r. Now, the type of force that we have acting here is going to be the force of tension. So this is going to be Ft, and then this is radius r. And we're representing our radius as a large r, which we'll just write here as a large r. Now, this was our Ft. Now, after this, we can use Newton's second law in rotations, which is torque net is equal to our moment of inertia times alpha. So then if we have that our torque net is I times alpha, we can set it equal to our torque. Our net torque is going to be our force of tension, which we can just call tension here. So this is going to be R times tension is equal to I times alpha. Now our moment of inertia was I is equal to 1/2 mass of the disk times radius squared. So this is going to be RT is equal to 1/2 mass of the disk times radius squared times alpha. Now, after this, what we can do is simplify by dividing both sides by r. We're left with T is equal to 1/2 mass of the disk times, you're left with only 1r times alpha. Now, how can we relate linear and angular acceleration? So because we have that the string unwinds, our acceleration is equal to our radius times alpha. Now alpha is going to be a over r. If we substitute this into our equation here, we have this as alpha. So our tension force is 1/2 mass of the disk times r times A over R. And you could also just write this as T is 1/2 mass of the disk. This is large R. What we see is that large R is going to cancel out. So this is just mass of the disk times linear acceleration. So we have tension that is going to create rotation, and part of that motion goes into rotational acceleration. For the free body diagram, we're going to have that the force of gravity equal to the weight is acting downward at the center of mass, and the force of tension is going to be tangent to the circle's radius, and that is going to act down because currently if the string is pulling down on the mass, the string also has to pull up on the disk according to Newton's third law. Now for part C, we are asked to find the acceleration of the hanging mass in terms of mh, md, and mr. Our first equation, we have mhg minus t is equal to mha. So we can substitute in our tension. Our tension is going to equal to 1/2 mdA, right? And if we sub that in here for tension, we get mhg minus 1/2 mdA is equal to mha. We rearrange our terms here. We have mhg is equal to mha plus 1/2 mdA. What we have here is we have a in both terms, so we can factor out that a. And we have mh left over, and we have 1/2 md is equal to mhg. So if we just solve for acceleration, we'll divide both sides by this. So we get a acceleration is mhg divided by mh plus 1/2, the mass of the disk. And what we can see from this formula is some forces accelerate the mass, and some forces accelerate the disk. We can do some limit checks. So for case 1, we look if md approaches 0, then a would equal to mh times g over mh, which would simplify to just g. So if you have no rotation, it makes sense that you would just have free fall. Now case 2 would be if we had md approaches a very large number, if md was huge. Then our acceleration would approach 0 because we would keep dividing by a larger and larger number. That would make sense because then the disk would be too heavy to rotate. Case 3 would be if we had mh approaches 0. So our acceleration would approach 0. Because that would mean we have no force to drive our motion. Because then we would just have multiplication by 0 up here, and we divide that number by another number, making our acceleration overall even smaller. Now we are asked to redo this problem using energy conservation instead of forces. So if we redid this with energy conservation, we can start off with the fact that the mass that is hanging is multiplied by our gravity and height. This is just our UG, is equal to our kinetic energy that we have that is translational, plus our kinetic energy rotational. Now, translational is 1/2 mass hanging times velocity squared, and rotational is 1/2 moment of inertia omega squared. We can substitute our I. So moment of inertia for the disk is 1/2 the mass of the disk radius squared. So this simplifies to 1/2 mass hanging velocity squared plus 1/2 this expression times omega squared. Now we can relate our V and omega when you have rolling or rotational motion. V is equal to R times omega. We can divide both sides by R, and you can see that omega is equal to V over R. So that means that here we have expression for omega. We have plus 1/2 times 1/2 mass of the disk times radius squared times V over R squared. So here we have an R squared here, and if we have R squared here, and we have an R squared here, that means that R squared would cancel out with the bottom. We have 1/2 here, so we can multiply 2 times 2, and that would be 4. This would give us 1 over 4 mass of the disk times velocity squared. So our full equation right now is the mass that is hanging times our gravity times height. And what we see here is we can currently factor out this V squared. So if we do that, we are left with 1/2 the mass that is hanging plus 1 over 4 the mass of the disk is equal to the mass hanging GH. If we solve for our velocity squared, we divide both sides by this expression. So we get velocity squared is equal to this expression. However, we know we have a kinematics equation that says that V squared is equal to 2 times acceleration times height. So if we know that, we can actually substitute this in for V squared on this side, giving us 2AH is equal to this expression. After this, we see we have H on both sides in the numerator, so you can cancel that H out. After that, we can multiply the denominator. So we have 2A is equal to mass hanging times G over 1/2 mass hanging plus 1/2 mass disk, which we basically just factored out 1/2 from our denominator. After this, we'll just simplify, which means we can divide both sides by 2. If we divide both sides by 2, we're just multiplying this denominator by 2. If we do that, that cancels that 2 out, and that cancels that 2 out. So acceleration is just mass that is hanging times g divided by mass hanging plus 1/2 mass of the disk. Again, our energy basically split into translational and rotational motion, so we still get the exact same answer. So rotation reduces acceleration by adding effective mass.